choice to introduce the two different W and U though?
Well, I was forced, right? I have here an implication, I have another implication. Implications are associative to the right. So I have two A's. Okay. Maybe that was a little silly, but that's a perfectly legitimate thing. It could happen.
We couldn't reuse, if we introduced W, we couldn't reuse it in the previous.
Sorry?
If we introduced W at the very bottom, we couldn't reuse it.
No, we cannot. Okay.
Yeah.
That would be amounting to overshadowing.
Yeah.
Okay. So think of every assumption you introduce must have a unique name. So that you have a way of accessing all the assumptions. So to be precise, all the names of the assumptions must be unique within one branch. Okay? So think about programs where you have some kind of form of pattern matching. Okay? Two different branches of your pattern matching, you could reuse the same variable names. They have nothing to do with each other. But you see that already I'm talking about concepts that you might have seen in programming, right? Overshadowing, scope. Okay, so clearly this does foreshadow somehow how this relates to computational ideas. Right? Okay, so somebody brought up context, and before I start with context, I have one more property. So this, I should say what this property is. That says I can reuse assumptions. Okay, that is the property called contraction. Which essentially says assumptions can be used as often as you like. So these are structural properties, again. Contraction and weakening are what we call structural properties. And, but I want to point out that this may not be always what we want. Okay? So in particular, later on in the week, I will talk about what we call substructural language. When you restrict two of these rules, these structural rules, structural laws, I should say. Because if you think of an assumption being a resource, okay, let's say money, it's very unnatural that I can use my dollar for more than one thing. Okay? It would be a great way. I can suddenly have $1 and spend it 100 times. Okay? But that's not how money usually works. Usually how it works is I spend my dollar and it's gone. Okay? So the fact that we have here assumptions that can be used as often as we like, okay, is a very particular view, okay, which does not necessarily translate to thinking about assumptions as resources for income. But for now, that's the prevalent view, I would say, in logic. And there's a third property of these hypothetical assumptions, which has to do with substitution. So if you have one of these hypothetical derivations, okay, so if we have a derivation of C being true, okay, under some assumption A true, okay, so this is a hypothetical derivation. And we have a proof E that says A is true. Okay, so there's some kind of tree here that establishes that A is true. Then you sort of can fit this in this guy. Okay, so you can take this and plug this in here. And essentially what that means is you eliminated the use of this assumption. So then we can eliminate the use of the assumption U by referring the proof of A being true. So that's what essentially what happens here. You plug in, instead of saying here I have this assumption U and I'm done, here you have justifications, right? A number of inference steps, and these are the number of inference steps that you're using in order to justify why A was actually true to begin with, why you didn't need to assume it. Okay, yeah.
Is substitution also called cut, or is cut different?
Cut is different.
Okay.
Okay, but it is closely related to cut. Okay? Cut is different.
Okay.
Yeah. Yeah.
Follow up to that, is this a special case of cut?
No. All right. So that brings me to context, okay? So because if you want to actually state these properties a bit more succinctly, we need to have a way of representing actually our list of assumptions. And so we will not only have propositions, but we'll also introduce this idea of the context. And this is where we differ from Jensen. Okay? But as computer scientists, you might find this quite intuitive. Okay, we want to actually do some bookkeeping explicitly, and not do this two-dimensional thing. We might want to actually implement a program that checks that our proofs are valid proofs. And so we will think of this context of assumptions as an unordered list. So this is the name of the assumption, and this is the judgment. It's unordered because we have actually a third property, which basically says the order in which we started introducing these assumptions doesn't matter. Okay? So indeed, I put them up there somewhere in space, okay, on the board, and then I cleverly kind of positioned them so that everything fell into place. Okay, but the order in itself doesn't really matter. Okay, so if I say A implies B implies A and B, it doesn't mean that, that the proof will look any different from B implies A implies A. So it's not a step. Okay, so some people might even think of it as a set. All right. So that means I can now reformulate these rules. Okay. I basically change my judgment by keeping my assumptions throughout. Okay, so that means now if the proposition A is true, okay, proposition A is true, given the context of assumption. And so here it's really just for bookkeeping. So nothing happens here. Okay, we'll just keep all the context around. And nothing happens. I'm not going to do this with its derivations, but something interesting does happen here in the rule for implications. Because what will happen here is that I'm not doing this two-dimensional thing. Okay? Instead, I will actually localize this assumption. Okay, I have some assumptions here to begin with, and now I'm going to add to it the assumption U. That says A is true. And I'm going to prove that B is true. Now I'm actually extending my list of assumptions. And I need, so let me move this rule over here, have a little bit more space. But I need one more rule. Okay? I need a rule that allows me to look up that assumption. Here, the way we use the assumption was sort of implicit, right? It's just floating around and I just grabbed it. But if I have an explicit context, I actually need a separate rule, which allows me to look up an assumption and establish a proof that says A is true. Okay. If I have an assumption X, A true in gamma. So this is the price I have to pay. I'll have to sort of make this more explicit. Yes?
Could you move up
The board?
this whiteboard a little bit, because I can't see where.
Yeah. That was very helpful. So that means now also I can state my properties for weakening, contraction, and substitution quite succinctly. So I can say weakening as a property, which will say that if I have a proof of A true, then I also have a proof of A true with this additional assumption B true in it. Okay. And I can say contraction. So if I have a proof of two assumptions, where it chooses two assumptions, X and Y, and it proves C is being true, then one of these assumptions suffices. And last, I can define my substitution property, which will say that if I have a proof that depends on the assumption A being true, and I have a proof for A being true, then I will have a proof of C being true. So instead of sort of justifying this by sort of in words, I can actually now establish these as theorems actually about these kinds of these rules. And if you have done proof by induction, these are sort of proofs by induction you can actually prove about. So last I want to sort of justify now why are these good rules to begin with? Okay, so how do these rules fit together? Okay, so, and the principle we're going to use is we're going to look at the combination of introduction and elimination rules to justify whether they fit. So the idea of looking at these combinations of inference rules and see whether they fit, essentially we look at two properties, local sameness, actually let me put it there. as local completeness. So local soundness will say a combination of introduction and elimination rules is not too strong. And so they don't allow us to infer more than we should already know. So they don't allow us to infer more than we already know. And local completeness says that the rules, the combination of introduction and elimination rules, is sufficiently strong. The combination of intro and elim rule is sufficiently strong. So what does this mean? Okay, so the local soundness for conjunction, we introduce and then we eliminate. Okay, so I'm going to introduce a conjunction. And then I'm going to eliminate it. Okay, so I introduce it, and I eliminate it. And it looks like I haven't really gained anything. So by design, this is a perfectly valid step in my proof I could do. But it looks like I haven't really gained much. Why? I haven't gained anything, which is actually a good thing. Because the information here I proved, okay, was A being true, was already present when I started my proof. Came in here. So this collapses, okay, to essentially using this derivation A to prove A is being true. So whenever you have this redundant combination of these rules, it can be collapsed into essentially a shorter derivation for A being true. And this brings us then also eventually to this question, is there a normal form of a proof? Is there sort of almost like the most compact form of a proof you could think of? But for just a sanity check, this is a very good check. Okay? It basically says we introduced and eliminated, we didn't gain any information. And we can do, of course, the same thing for the other elimination rule. So there's a second elimination rule, that is the fact that we have B true. Okay. We introduce and we eliminate. And we haven't really gained anything. Okay. Good. Here we have this derivation E this time. It's the same thing we need to prove, and therefore, yes, okay, we have a proof of B true to begin with. And we didn't gain anything. Now, for local completeness, okay, it's the opposite. And you need to essentially justify starting from a proof of A and B. We can rebuild the proof of A and B. Let me erase this last part and add the completeness part. So we start with a proof of A and B. And we ask him, can we expand it, okay, into a proof for A and B, using the fact that we have A and B. So, the way we're going to establish this, saying A and B, in order to prove this, we need to prove A and we need to prove B. Okay, so we have here A true and B true. And how do I know I have a proof of A? Well, that I have because I have my elimination rule that allows me to extract the left side. And luckily, I also have my right elimination rule. Okay, so both elimination rules are necessary because I now need to also extract the right elimination rule. So if we would lack one of these elimination rules, it would not be sufficiently strong to rebuild essentially my proof I needed.
Weird fuzzy question, but it seems strange that we need a left rule and a right rule. Is there like a setup where you just have one rule? Yes.
Indeed there is. You'll see that later on. In fact, it makes sense to have both of these rules there. Yeah?
So it seems like in this setting, we need to place some constraints on our proof tree, right? Like if we want to show that we can infer that A and B is true, like if we, in the second example, if we reached back up into the hypothesis and just kind of grabbed alpha, that would sort of, like that would be a valid proof tree, but it wouldn't demonstrate the property that we want.
Here?
Yeah.
Well, you would need to discharge your alpha, so the alpha would suddenly be new.
Oh, I see. Okay.
Yeah?
Well, two questions. The first one is that it's like, is there like a constraint on, like, you know, this is a nice
Yeah.
proof theory, but like, are there constraints for like weird, more exotic sort of theories or like logics where like your proof tree has to be a certain size or something like that?
So we don't usually put constraints on the proof tree has to be a certain size, but if we are playing with these structural properties, there is a close relationship because you get that sort of as a derived property because you have, if you omit weakening, okay, and you omit contraction, it means that all the assumptions must be used exactly once, and we know that this corresponds to polynomial time computation. So there is, because of the fact that we have to reuse every assumption once, it also gives us in some sense, I guess, a bound on some of these proofs, if they're normal. Okay. But it's not something we typically bake into the proof system itself.
Okay.
Does that make sense?
Yeah.
Yeah.
Sort of a follow-up. Can we still use this type of proof tree if we omit the exchange rule or not?
Yes.
Okay.
Then this rule, this variable rule, will change.
Okay.
Because here I say I look it up anywhere. If you have exchange, you say you have to look it up on top. If you don't have contract, if you don't have weakening, then you have to have used up all these assumptions. It can be only the last assumption left. Okay. So we'll play with this in my third lecture or fourth lecture. Okay. There's one last question. Yeah.
Is there a more formal definition of this locality you're talking about? And these are like
Is there a more formal definition of?
definition of this locality you're talking about. And
The
these
locality.
are the hints of how, like, what the definition is, or is it a loose term? And these are like how it can be interpreted.
What kind of locality?
The locality of soundness.
Local soundness.
Because at one point, like we
Maybe
have semantics to measure soundness and completeness of the system, right?
Sorry?
But in some viewpoint, we have the semantics to measure the soundness and completeness of the system. So I'm kind of like, I don't see the connection, like what exactly do you mean by local soundness?
So for now, I just mean that the combination of these rules don't mean gain it's local in the sense that I only consider the interplay of the introduction and elimination rule of conjunctions. I don't have a global soundness property, right? I don't know whether the system globally makes sense. I only know locally, if I look at these two rules, they seem to be sensible. Now there are certainly philosophical discussions, okay? So in particular, Belknap has this great paper, Plonk and Tonk, whatever. So he defines these prepositions called Plonk, and then he does local soundness and says, is this a meaningful logical system? And one might argue no. Okay, what's Plonk and Tonk to begin with? Okay. So yes, okay, there are certainly other things that feed into the fact that this is a sensible system. So think of this as one thing in your toolkit to justify why something is sensible. It's something, an easy check. Okay? It's something you can do right away. And this afternoon I also talk about how this relates to computations. So it is a very sensible and very useful check. But it's a weak form, okay? So I'm not saying anything about the global consistency of the system. And in fact, Gensen did not justify this with these local soundness and local completeness properties. It was really something that later on people sort of thought about what does it make for a system to be harmonic and why are the rules he gave are sensible and so on. If you go to philosophy of mathematics, they talk about these things. So Dammit is one of the people who sort of came up with this idea of harmony, and harmony is sort of by coming up with these kinds of rules that have a nice interplay. But it doesn't justify that I should have picked these particular elimination rules. Okay? So there was somebody I should have a different elimination rule, for sure, and that would also be locally sound and complete. Okay? But it does justify that the rules I have here on the board are, sensible in this limited sense. Okay? And to finish, maybe I'll do this for implications as well. Okay? So for implications, we introduce and eliminate. Okay? So we have here X, A, B true. And we introduce, okay, so that gives you A implies B is true. And I have the proof of A as being true. Okay, that gives me the proof of B is true. And so now I need to somehow say, so this is local soundness. That I had a proof of B true to begin with. So why did I have a proof of B true to begin with? So now it's not as trivial as in the conjunction example, but I can observe, right, that I have here a derivation that depends on this assumption A being true, and I do have here a derivation of A being true. And so I can use this substitution property I have here to justify that, yes, okay, I have a proof of B being true, okay, and this is by the substitution property using E and E. So this lemma over there, which I haven't proven, just say it, is essentially used in order to justify this step. And why is it locally complete? So I have a proof of A implies B. And I want to show that indeed, okay, I can rebuild the proof of A implies B from this proof of A being A implies B. So I'm going to introduce an assumption. and I need to prove B is true. Okay? And how do I finish this little derivation tree in order to justify that B is true, given this assumption that A implies B is true? Okay, so I want to use the elimination rule for this. Okay, and I'm going to use the fact that I have A true, proves A true. I do X. Okay, yeah. So what is missing? Well, I need a proof that says A implies B is true in order to use the elimination rule. Okay, and I get to that by using this is what I started with, and this is weakening. So weakening allows me to have these additional assumptions. I don't care. And then I can actually conclude that I have it still prove A implies B, no matter if I have this additional assumption there. That's actually called it B. And that means now, yes, okay, I also essentially rely on weakening in building and justifying this. So, so this means yes, okay, it is globally, locally complete. And what I want to do this afternoon, and I want to revisit this calculus, but I want to give to each of these propositions a proof term. I want to associate to each of these propositions a proof term that internalizes this notion of the fact that the proposition A is true. And that gives us essentially this view of thinking about propositions as types and proof as programs. And so we'll see this for disjunctions hopefully in the afternoon. And we'll see also that out of these local sentence properties, for example, falls sort of a reduction rule that gives us computation on the level of programs. And so, so then I will talk more about like the implications of this idea, and in particular what it means to sort of normalize these kinds of programs. And then the third lecture I will actually give you a proof of how to prove normalization. So we'll do a simple proof, but if you're then more interested, you can look, for example, at our paper, Poplomart Reloaded, which gives a strong normalization proof. But